Welcome back, physicists! Today we're going to be discussing two-dimensional waves because up until now, we've been talking about waves in one dimension. We've been graphing these waves and putting them on strings where they just kind of travel like this, right? And it's fine. And if you look at it from above, it looks like a straight line because it's in one dimension. It's a one-dimensional wave, but not all waves are one-dimensional. Unfortunately, I wish they were. That would make physics so much simpler. But we have good old wacky water. And we hate water because water gives us two-dimensional waves. Now to give you an idea, imagine you toss a pebble in a lake again. You remember that analogy from the second video? Yeah, I'm doing it again. If you look at it from the side, the wave looks like our typical sinusoidal wave. It looks like that, right? That's what happens as the ripples keep traveling through the water. However, if you look at it from above, get kind of a curvy shape here. These lines. These lines are called wave fronts, by the way, and they represent either the crest or perhaps the trough of the wave. So either here or here. And really a wave front is any line that connects crests or troughs of a wave in a continuous line. And so that makes these waves two-dimensional. Two-dimensional. Which is kind of crazy because that sort of changes how we think about them. To demonstrate, how do these waves form? Well, our good old buddy Huygens, you might know the Huygens-Cassini probe that went to Titan, but Huygens was an actual physicist. And our good buddy Huygens came up with a model for wave propagation. And his idea of wave propagation is that a wavefront is actually made of an infinite number of little tiny wavelet disturbances that just keep on expanding and propagating, and oh my gosh, they're everywhere and they push the wave forward. Right? That's Huygens construction. Now, this doesn't really explain everything that has to do with waves. In fact, as we get more complicated, things don't really start to work out with the Huygens construction. He gives no explanation for the fact that it only moves forward. I mean, if it's an infinite number of propagations, it should move out in all directions, right? But it only moves forward. So, but we don't worry about that. For the purposes of this course, Huygens construction is absolutely correct. Don't question it. Don't listen to the science channel. Gosh darn it. All right. Well, we're looking at these waves, these water waves. How about we analyze them in context of those 4 key tenets of waves that I mentioned in the wave video. How about reflection? Yeah, you remember these, right? I mentioned them like once and then we never came back to them, but now we're going to come back to them all the time. Ha! Coming back to bite you. So what happens when a water wave reflects? Well, if you have a circular water wave, which means you dropped your pebble in a lake and created a circular disturbance, and it hits a barrier, then it's going to create a sort of like inner circle, because the barrier is going to become a new source of infinite disturbances. Little wavelets that are going to add on to each other to create a new wavefront that appears inside the circle. And that's how water reflects when it's a circular disturbance. However, if you have like a wave crashing on the beach sort of situation where you have a more straight wavelet, well, what's going to happen here is the barrier becomes the source of a new disturbance and it's going to bounce off. Still going to be straight. However, in this case, it's going to make the same angle. Let's say this is 30 degrees. Well, this one's going to be 30 degrees, just going in an opposite direction. But it's the same angle. Now, when we go into the area of refraction, things get a bit more complicated. So let's say you're moving from deep water to shallow water. Well, a fact about water, when it moves from deep water to shallow water, waves of water, they slow down. Let's say you've got your line here between the deep and the shallow. You got a wave. That wave is traveling to the shallow. There's nothing it can do to stop it. Well, that wave's going to bend a bit. It's going to change directions, just ever so slightly. And there's going to be a new disturbance that moves a bit slower. If we were to draw these waves in terms of wavelength, this one would look like this, but the wavelength for this would be a lot more frequent. However, the frequency of the wave is the same, so that means because wavelength decided to go ahead and increase, but frequency is the same. That makes friend speed slow it. So they decide to move slower when they go into these smaller area. So the wavelengths are shorter. See, they're smaller. There are more wavelengths, which means that the wavelengths are smaller. Now, how do we calculate the angle at which the wave bends? Because we have to be able to calculate that, right? There can't be things in physics that we don't know. And you're absolutely right. Here comes our good old buddy, Snell's Law. Now, what Snell's Law explains to us, what our buddy Snell came up with, is the sine of the angle of incidence, sine I, over the sine of the angle of refraction, sine R, is equal to the ratio between the initial speed and the refracted speed of the wave. Now, however, the angles of incidence, the angles of refraction, are not measured to the barrier of refraction. They are instead measured to the normal. What is the normal, you may ask? And the normal is simply a line. Think how the normal force is perpendicular to the surface, right? That's the same thing with the normal. The normal is perpendicular to the line of refraction. So if you have a wave coming this way, it refracts off kind of like that. That's your angle of incidence right there, and that's your angle of refraction. And that's the basics of Snell's Law. I would go through an example, but I feel like it's a pretty simple ratio sort of situation, so we don't really need to go through an example with Snell's Law. It's not super crazy. Now, how about diffraction of water waves? What's the deal when water waves decide to diffract? And that's pretty straightforward. When we get to diffraction of water waves, if it's going through a small hole, got all your waves coming up, that small hole, even if you have a long, straight wave front, is going to act as a new source of waves. They're going to propagate straight from that hole. If it's longer, it's a larger hole per se, well then more of that's going to be straight. But it's the same idea. And the same thing happens when we get to a barrier. Let's say you got your straight wave fronts approaching here, going down. They're going to part around the barrier, and when they reform, there's going to be a gap. And so little wavelets are going to rush to fill it. And you'll get something along that, which will fade as you go along with time. But that's the idea of going around. And finally, the final property we have to discuss when it comes to water waves is the idea of water waves interfering. Interference. And interference of water waves is pretty straightforward. It's the same as like wave pulses. If you have two water waves from the side, they're in the same sort of, that are in phase, right? They will combine constructively. However, if they're out of phase, if they're like opposites, like this one, they'll combine destructively. That's sort of the idea. However, what if you have two water wave sources? Like source A here that's creating a bunch of waves, source B here, that was a horrible B, is creating another source of waves. Well, what happens then by view of the wave fronts from the top? Well, that creates an interference pattern, which is way too complicated to draw, so I'm just going to show you the picture that the book gives us. Looks a bit like that. That is the interference pattern. Now, why is that? Well, the book also gives us a handy-dandy picture about that. And the reason for that is that sometimes the wave paths will align so that they combine constructively, as in these cases, creating bigger waves. However, other times, the wave paths will align in such that they combine destructively, creating these kind of fuzzy areas where there aren't any waves anymore. And that is the idea of interference of two sources of waves. Well, you may be asking, can we calculate whether or not that'll happen? And yes, we can, with path difference and phase difference. The basic formula for phase difference is if you have path difference d in meters, however far apart your starting points are at any given point, right? So here or there, right? And you have the value of pi, right? And you have your wavelength of lambda, then the angle of phase difference, which is basically when they collide, how different the angle is, which tells you whether or not they're colliding constructively or destructively, equals 2 pi times the path difference over the wavelength. That is the phase difference formula. You probably won't have to use it much, but it's always handy to know. And that is all I have to say about two-dimensional wavy waves. Next, we'll be talking about sound.